All right, Mr. Dooley just got done talking about potential energy due to gravity. And we see that the formula for potential energy due to gravity, mgh, is exactly the same as a formula that we had for lifting something and how much work was done. The weight, mg, which is our force, times the height, which is our distance, force times distance. So that's a great intro to the work-energy theorem. And the work-energy theorem is just telling us that work and energy are interchangeable. And we saw that with potential energy. So when we talk about work and energy, the work done on an object is equal to the energy that that object gains, or the work done by an object is equal to the energy that that object has lost. Whether that's kinetic energy or potential energy is dependent on the situation. So that tells us that work is equal to the change in energy that object has. So we can have either or, sometimes both, a change in potential energy or a change in kinetic energy. If we have a change in kinetic energy, that means the velocity changes, because we're not going to change the mass by putting a force on something. If we have a change in potential energy, that means the height changes, because again, we're not going to change the mass or the acceleration of gravity by putting a force on something. All right, so those two formulas, delta KE or delta PE, can be expanded on a little bit, because we know kinetic energy is 1/2 mv squared, and we know potential energy is mgh. So when we're talking about change, we're talking about final minus initial. So we can say that the work energy theorem is FD equals 1/2 mv final squared, the final kinetic energy, minus 1/2 mv initial squared, the initial kinetic energy. The mass doesn't change, the mass, or the 1/2 stays the same. In fact, we can factor out 1/2 m and just have v final squared minus v initial squared if we want to. Same thing with potential energy due to gravity. The work done is equal to the change in gravitational potential energy, so the mghf, the final, minus mghi, the initial. Now, we can have a decrease in energy, and that would be the final energy is less than the initial energy. That means you've slowed down for kinetic energy, or you've decreased your height for potential energy, or we can have a positive delta energy, and that means we've sped up for kinetic energy, or we've increased our height for potential energy. So let's give an example here. Along with the football theme we've been dealing with, Dalvin Cook, all right, Vikings running back, he's at top speed, 9.48 meters per second, and a silly little corner tries to tackle him. For those that you don't know, a corner is a cornerback. They're the defensive backs. They're little. They have a tough time tackling a big guy like Dalvin Cook. So the cornerback can only slow him down to 6.33 meters per second. All right, he hasn't stopped him, but he has changed his potential energy. So previously we saw Dalvin's mass. So now we can find the work done by the cornerback in slowing down Dalvin. And we use the mass of Dalvin Cook and find his final potential, or final kinetic energy, which is based on his final velocity, 6.33 meters per second, and subtract that by the initial kinetic energy that he has, which is based on his initial speed of 9.48 meters per second. So in other words, he slows down. So we should expect a negative kinetic energy value and a negative amount of work done by Dalvin. All right? So I'll give you a moment here to figure this out. You can hit pause and try to solve it. All right. So here's what we got. We got final kinetic energy minus initial kinetic energy is equal to work. So we can do 1/2 mv final squared minus 1/2 mv initial squared. And as you can see, we factor out the 1/2 m because that doesn't change. So from the previous problem, we had a mass of Dalvin Cook of 94.8 kilograms. So take half of that and multiply that by the difference of 6.33 meters per second squared minus 9.48 meters per second squared. And we get a work done by the cornerback of 2,360 joules. That is the decrease in Dalvin Cook's kinetic energy, that means the work has been done to slow him down. So the work that he's capable of doing has diminished by 2,360 joules. All right. Now, what if, as this corner was holding on to Dalvin and trying to slow him down, he dragged him for another 3.5 meters? Well, now we know the change in energy, or the work done, and since work is force times distance, we can find how much force the corner was using on Dalvin. All right, and we can just take work equals force times distance, divide the work done, which we just calculated, by the distance, 3.5 meters, and we find that the force that the corner put on Dalvin as he dragged him was 670 newtons in the opposite direction. So this is just an example of that. So what you want to look for to solve these problems is a change in speed, if you know the initial and final velocities, the mass of the object. Generally, you'll be solving for a force or a distance, but if you know a change in speed, you can find a change in kinetic energy as long as you know the mass of the object that is changing its velocity. Once you know the change in kinetic energy, then you can use that and set that equal to force and times distance. We do the same thing with height and gravitation. The work done to lift something up is equal to the gain in kinetic or in potential energy that it has. Or if something falls, how far it falls tells us how much potential energy it's lost. That means gravity's done that amount of work on it, or it can no longer do that amount of work that it had before. All right, so that's what we want to stop with there. We got some problems for you guys to do on these, and good luck on that. Thanks.